Right, so our final timetabled speaker before we move into the lightning talks and the closing discussion is Guannan Wei. Please take it away.
As we all know, WebAssembly is a stack-based low-level IR, and it's pretty fast, and it's already supported by all those major browsers. And one nice thing of WebAssembly is that it offers official specifications from its beginning, and it has a reduction semantics for the dynamic semantics, and also static type systems, and constraining the shape of the stack, and also those meta-theory result also follows from the formalization. And another nice thing is that there are a lot of ongoing work and new features adding to WebAssembly. For example, effect handlers or stack switching, which has been mentioned multiple times in today's workshop. But let's take a closer look of the reduction semantics. And it's basically specified as a transition between configurations. And each configuration has a global store S here, and also a list of values, which are those values for local variables, and also a sequence of instructions. And we can specify the transition for that. An example here shows is how loop works roughly. And we have a loop and it has the body of the loop. And when we go into the loop body, we will kind of copy the body of the loop and using an additional administrative instruction called label here, which stores what the loop body is. And later when we have a branching instruction inside of the loop body, we're going through to search what the corresponding label to jump back to. And then we expand the syntactic structure along the transition of the configuration. And this is explicit by two-modal evaluation context. It's also quite verbose. And this duplication about the syntactic structure and searching through the stack, it's causes a lot of inefficiency if you implement it naively, especially for deeply nested frames or labels. And more importantly, the style of semantics defining as small step reductions is not compositional and also not tail recursive. So because it's not compositional, originally we want to do something like partial evaluation or program transformation. This has become a bit tricky or not ideal to deal with. And also because it's not tail recursive, if you want to implement this style semantics in a function language, it's not ideal for performance or space consumption as well. So alternatively, we look at the semantics of WebAssembly, and we want to reconstruct a semantics using continuation passing style, which means instead of using first-order representation for the control construct, we can use continuation function in the meta language to represent the control structures or control semantics. And what we eventually have is a compositional and tail recursive semantics for a subset of WebAssembly in continuation passing style. This semantics can be implemented as an interpreter pretty much straightforwardly, as a big step interpreter, or you can also view this semantics as a transformation from WebAssembly to lambda calculus. Now, before going into the details of semantics, I just want to quickly going through a subset of WebAssembly where we have labels, identifiers are both natural numbers, and those ordinary data types. And for instructions, we have those instructions manipulating the stack. We have instructions to get and set local variables, instructions for structured control flow, the block, loop, and conditionals. We also have branching, function call, and return. And the function body basically containing a list of instructions, and the top level of a module is just a list of functions. Okay. And what we really want to do is to define such a semantic function, the semantic brackets, that maps a list of instructions to another function. And here I showed the signature here. The semantic brackets takes a list of instruction and producing another function. And this another function takes a stack, which is the list of values or represented by a list of values, and also an environment. And this environment is really just, we use it for local variables. And additionally, it takes a continuation. And this continuation is a function that taking the current stack and also environment, producing the answer type. And we explicitly leave this answer type abstract so that user can customize a little bit. So far, this is really all standard, right? Nothing really special. It's just a CPS interpreter. But what's really new here is that we need to add additional trail component to the interpreter, which is a list of continuation, or we use it as a stack of continuation, which we will go into details to see how we provide such values and use those values. And because our semantic function takes a list of instructions, we were just going through all possible choices here. And the first one is that the list of instruction is really just an empty list. And in this case, we have finished the current computation. And the natural choice is really just to call the continuation, which is the kappa here. And but later we will see how this coming from. But this is a simple case when the list is empty. Okay. And the next group of instructions is really just manipulating the stack. For this no op, we just recursively applying the semantic function on the rest of the instructions, right? And for the constant instruction, we just get the constant c value c and push it on the stack, and then recursively calling the rest. And for add, we assume we look at the stack, and there's already a value of v1, v2 on the stack. We add the result, and then calling the semantic function on the rest of the instructions, right? And similarly for local variables, get and set, we just access the variables from the row for get, and for the set, we just update the environment row with the corresponding value retrieved from the stack. Okay, so far this is really all simple, straightforward stuff, and we haven't really used the continuation or the trial neither. Then we look at the semantics for block and branching or break. And here the block takes additional annotation about the type, which takes the input type, the input arguments and output arguments on the stack for the block. And the block body is this ES, which is a list of instructions, right? And how should we define the semantics for that? Before going into the formalization, let's look at informally how those things work. And the first thing is that those blocks, they are structured and they can be nested. Here on the right here, I showed example here. We have a block, and inside the block we have another block, right? And important thing here for the block is that a block has a label, and this label can be either named, like L1, L2 here, or just the nameless as the Brown indices. And more importantly, those labels, they serve as a branch target. So inside of a block, we can have this BR instruction that referring to that label introduced by the block, meaning that we want to jump to that somewhere introduced by the block. And for the block semantics, we're really just jumping to the end of the block, right? So the idea here is that we need to remember the escaping continuation once we are going into the block, so that if there's a BR instruction inside the block, we can just discard the rest of the continuation and jump to that. Okay. Then into the definition here, we're really just defining the kappa 1 as this escaping continuation by which recursively calls on the rest of the instruction. And this is just a recursive call on rest. And the important thing here is that this kappa 1 is used as both the ordinary continuation and also appended on top of the trail. And then at the later point, if there's a BR instruction inside of this block, we'll just use a corresponding label to retrieve that continuation from this trail and just invoke it. Okay? So the next thing is we want to look at loops. And similar to blocks, loops also introduce a label as jump target, but different from blocks, those branching targets introduced by loop will jump back to the beginning of the loop. This is different from those jump target introduced by the block. And here, the example shows we have a loop L1, and inside of the loop body, we have a nested block L1, L2, and there are branching instructions jumping back to L1 here. And if there's no branching happens, then the loop finishes. We're just going through the next instruction right after the loop. Okay. Then the idea here is we need to have two different kinds of continuation. One is just following through to the immediate next instruction, and the other one is to going back to the loop. So this idea can be also expressed straightforwardly in our formalization, where we define first this kappa 1 is the just following through continuation, capturing the rest instruction of the loop, and also there's a kappa 2, And kappa 2 is both the body of the loop and also the branching continuation for this loop. And note that this kappa 2 is defined as a fixed point or recursive function, so that inside of the definition of kappa 2, we're appending kappa 2 onto the trail as well, so that later if there's a BR instruction inside of the loop, it will goes back to the original point of the loop here. Okay. Then we look at function calls, and it's kind of similar to blocks, but we need to retrieve the function body. We just use this auxiliary function lookup function to get the function body. And there's also this build environment to construct an environment containing argument for this function. We define this kappa 1, which is a continuation for this function call, meaning that we're recursively applying the semantic brackets on the rest of the instruction right after the function call. Okay, but the important thing here is when we go into the loop body, we use a different trail. And here, for the function call, we use a singleton list that only containing this kappa 1. And this is because those escaping continuation introduced by block are local to a function. When we go into a new function, we can just discard the current trails. And the return instruction is interestingly just calling the last continuation in this trail. And because this is always introduced at the last element here, then we can safely call it. And we can sort of treat it loop return instruction as a syntactic sugar to BR. We're always branching to the topest level inside of function, the jump target here, which is always the last element we have in this trail. Okay. Now we have demonstrated this core CPS semantics for WebAssembly, and this trail constructing nicely gives semantics for both block, loop, BR, call, and return. And it is also compositional in the sense that every time we call the semantic brackets, we are calling strictly a subcomponent of the syntactic construct on the left-hand side. It also tail recursive in the sense that every semantic brackets call is used in a tail position. So now, what is really good for? So of course, we can try to use the semantics to specify other extensions or other construct in WebAssembly, which we did. I will show that later. And also because the semantics is defined in a compositional way, and we can treat it as equations. And we can use it to reason about certain behavior or programs in WebAssembly. And the semantics can be implemented straightforwardly as an interpreter, basically in any function languages. And one of the things we want to do, but we haven't, is to build a partial evaluator around this semantics because it's compositional, so it supposedly would make things much easier. So there are a couple of extensions I want to mention. We model several things. Structure loops, some of them are really hypothetic. It's not really in WebAssembly, but we just suppose we add this syntactic construct, how can we give semantics instead? The first thing I want to show is this tail call instruction. It's modeled after the current tail call proposal for WebAssembly. And by using this tail call instruction, we can explicitly enable optimizations for tail calls. And here we just model a very simple instruction, this return call. And the semantics in our framework can be straightforward because we already showed the semantics for function call. And here we just loop out the body of the function and build a new environment. But we are giving a different kind of continuation here. Instead of constructing a new continuation, coming back to the instruction of rest, we are just using the last escaping continuation on the trail, which is the theta last, and to pass into the loop body. Meaning that if there is a return instruction inside of the function body, we are returning directly to the caller of this current function frame. Basically, we're discarding this function frame and never coming back again. So we're jumping one more level here. Okay. And more interestingly here, as I mentioned, the semantics is compositional, and we can also treat it as a set of equations. We can justify the semantics I just showed here by calculating it from the semantics of return and call. And supposedly, we put a call instruction here, is call x, and right after that, we have a return instruction. So this is really a tail position of this function call. And we will do this calculation by just unfolding the semantic brackets and firstly unfolding the semantic brackets on call X, right? And we have basically copied the definition I just showed before. And then we still have the recursive application on the return and rest, this is shown in the blue here. Then we further unfold the definition of return, showing the lower part here, and we just basically copy the semantics of return here, and we call the theta last here. And one more thing is a little bit more reasoning is guaranteed from the type system, that we can further show that this kappa 1 defined in the upper part of my slides, calling the theta last, is really just the eta expansion of theta last, because it's additionally manipulating the stack, and those manipulation can be shown to be idempotent. So we can really just inline kappa 1 here and just replace the call of kappa 1 just to theta last. And eventually we have exactly the same definition as I just showed before. So this is a powerful way to reason about semantics by equational reasoning. And another extension I want to briefly talk about is a bit hypothetic, about resumable exception, or you can also think of it's really just effect handlers with just one unlabeled single operation. We extend the instruction with a try-catch block, and the try block is ES1, and there's a handler in ES2, and inside of ES1 we can throw an exception or perform an effective operation, and in the catch block we can resume back to the point where we throw this exception. So one of the example here is we have a try block, and here on line 5 we have a throw instruction, and with the error code -1, and then the control flow is transferred into the catch block. And once transferred here, on top of the stack, we have the error code and also a function value on top of the stack, and this, which is a resumption. And we can consume the error value, and then we call resume. This resume instruction, we're going back to line 6 here. And this is basically what we call resumable exception. And so the problem is, how can we express this behavior? Of course, there are already existing work on WASM effects, but here we kind of looking at traditional work in continuation passing style. And the idea is to extend our continuation with meta continuation, which means a continuation function also takes its own continuation. And here you can see the kappa continuation takes a meta continuation m count, and m count is really also the previously defined continuation. And we also have a handler value here, which can be used to handle the exceptions here. We can give those semantics here. I won't really go into details, but just to show that this something could be work here. We also have ongoing work on modeling WASM FX in this style using continuation, and we do already have a working implementation to run those programs with that WASM effects. And the idea is a bit different using meta continuation, but to use a different another trail of continuation so that we can manipulate the fragments of those continuation more easily. This handles this WASM effects is a combination of deep and shallow handlers. The formalization is still work in progress. And all those extensions we have implemented in Scala with the parser. And the current work is to validate our implementation and semantics against the official WebAssembly test suite. So some of the future work idea is we're interested in some sort of interderivation of mechanization of semantics here. And there's a well-known correspondence between big step semantics, CPS semantics, and small step reduction semantics. It would be nice to show that those semantics are really just can be interderived, for example, from the official WebAssembly specification. And the spec tech work is also interesting. We would like to see if we can derive what we have by hand in some mechanical way using spec tech. And a mechanization of our CPS semantics in a theorem prover would be also interesting, which then we can justify our equational reasoning with a higher degree of confidence. Of course, I think there are more interesting work can be built on top of the continuation passing style. So to summarize, we have developed a CPS semantics for WebAssembly, and we use a stack of continuation. to give semantics for block, loops, branching, call, and return, and the semantics compositional and tail recursive. And we have implemented this thing as a big step interpreter, but you can also use it as a compiler or transformer into a CPS form of lambda calculus. There are several possible extensions can be expressed in this framework. Some of them are hypothetic, and we showed that. Some of the ongoing work is to model WASM effects using this style. We have an accepted paper in the proceeding of trends in functional programming, and I think it's probably going to be the camera ready in February. Yeah, I think that's the end of my talk. I'm happy to take comments or questions. Yeah.
This is very nice.
Thank you.
I think you answered probably my question on your previous slide, but I just want to check.
Which one?
My question was going to be whether you proved any kind of correctness result here, and it sounds like you haven't yet.
Not yet. That's why we mentioned it would be nice to prove things in COG or any theorem provers about the correctness.
It'd be really cool if you had some sort of automatic way of taking the spec-text specification and generating a CPS transformation from that, but that seems quite ambitious.
That's true, yeah. Very interested in looking at that, yeah.
Hi, cool talk. I was wondering, on I think your first slide, you talked a little bit about like the motivation for doing this and how the small step semantics are kind of inefficient and whatnot.
Mm-hmm.
Are these small step semantics what WebAssembly implementations look like in practice, or is this like CPS transform? Is this compared with anything else, I guess?
So the small step semantics is not using a industrial scale implementation, but there is an official like reference interpreter implemented in this style, written in Camel. But I guess I wouldn't say the performance is good. I actually hope the way if you implement it in this way would be better performance compared to the official OCaml interpreter, and with similar or even less effort.
I guess kind of a follow-up question is, what do the existing big step semantics interpreters look like?
I think Conrad has a work kind of like big step semantics for WebAssembly.
Yes, although I never tried to make it executable. That was just to power up program logic behind the scenes. All of the interpreters I've worked on have been either small step or there's this concept of pretty big step, right, that Philippa and some others here might be familiar with.
Mm-hmm.
I've worked on interpreters like that. I've never worked on an actual big step interpreter.
Okay, then probably this will be the first one.
Yeah, I think you can totally own that.
Yeah.
We have one more question. One more question, then I think we'll move
on. A different question. One of the extensions being worked on at the moment for WebAssembly is threads.
Uh-huh.
Have you any idea how something like this would fit into threads?
Honestly, I haven't looked into details of that, but I would suppose it's possible.
Cool, thanks very much. Let's thank the speaker one last time.
Thank you.